Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called modeling competitive energy markets. The predictive artificial intelligence models are implemented in the General Algebraic Modeling System, GAMS, and use IBM Plex as the optimization solver. The two companies are business partners of HI. HI is a company at the forefront of high-performance artificial intelligence. The physical world and the economic world. In every real system there are two strongly related visions, the physical and the economic. The interrelationship is so strong that mathematically it is totally defined independently of our understanding. In optimization models, the formulation of the primal model of a system corresponds to our economic interpretation of the physical world. The associated dual model corresponds to the implicit view of the economic world. Central planning and the market economy pursue the same goal: the lowest economic cost to provide the service. The main features of physical world are primal vision, known, mathematical models, laboratories, quick reaction, rapid recovery, controllable, manifestation, activity levels, control centrally planned systems. The main features of economic world are dual vision, little known, mental models, no laboratories, slow reaction, slow recovery, not very controllable, manifestation, value of resource, control open markets. The view that prevails in both worlds is different and is associated with the mathematical problems that are solved. The primal vision minimizes the production costs of physical activities. On the other hand, the dual vision maximizes the value of the producer's resources, that is, his wealth. According to the duality theory, the two positions give the same results. The market players are agents, determine the decisions that maximize your income, to the extent that they have a greater knowledge of the behavior of the market. Normally they are generators, marketers, distributors and transporters. Regulator, responsible for market regulation. Operator, responsible for the operation of the market and the system. Supervisor, analysis of agents' positions to understand and manage the market power. Studies on the equilibrium of markets go back many years. Robert Dorfman, Paul Samuelson, and Robert Solow are best known as the co-authors of the landmark 1958 book, Linear Programming and Economic Analysis, commissioned by the Rand Corporation. This text was the first comprehensive treatment to bridge the gap between standard economic theory and the post-war developments in linear programming. It is considered a classic in mathematical economics for integrating traditional theory. It connected linear programming to classic theories of the firm and general equilibrium. Game theory. It explored interrelations between von Neumann's theory of games and linear programming. Input-output analysis. The book provided a rigorous mathematical foundation for Leontief's input-output models. Samuelson and Solow were awarded the Nobel Prize in Economics. All science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Those interested are encouraged to watch the video. Fundamentals of Optimization and Economics. Market modeling. Market modeling. Those interested are encouraged to watch the video. Modeling markets. Cooperative, regulated, and Stackelberg equilibria. The document present a general methodology to study the electricity market of a country or region, under various pricing mechanisms. The approach is based on modifications of a large-scale techno-economic model and is applied to a realistic model for the province of Quebec. Mathematical programming and a new decomposition procedure are used to simulate different electricity pricing schemes and their effects on the producers' and consumers' decisions. Three types of pricing are discussed, each corresponding to a different equilibrium. Marginal cost pricing, which leads to cooperative equilibrium. A related function of marginal cost, which leads to a regulated equilibrium, and monopoly prices, chosen by the producer to minimize its costs while knowing the optimal reaction of consumers to the proposed price of electricity, Stackelberg type equilibrium. The graph presents the structure of Quebec's energy system. 3 equilibria are described: cooperative, regulated, and Stackelberg. A real, large-scale model used by Girard in the province of Quebec is presented. The graph shows the market equilibria under the cooperative equilibrium, which maximizes the social surplus, equivalent to a perfect market. The figure presents the inverse supply function, which can be altered by the different types of equilibrium. In this case, the inverse demand function shifts upwards, the cost increases for fiscal reasons. The graph presents the Stackelberg type equilibrium, which is called a tempered monopoly. All 3 cases alter the equilibrium point of the market. The shaded part indicates the surplus captured by the generators. The average size of the problems, published in 1997, is presented in the table. The table presents the surpluses produced in the 3 cases. In this case, the best thing for consumers is regulated equilibrium, and for energy producers, the cooperation. This assumes that consumer demand is elastic. The graph shows the electricity exchanges of the 3 cases. The figures show projected residential heating consumption through 2035, for natural gas for residential heating, and electricity for residential heating. This is an example of what can happen in the planning of a market, when it is done with complex mathematical models. A large-scale energy economic equilibrium model. Case, NEMS, National Energy Modeling System. The National Energy Modeling System, NEMS, is an integrated energy economy modeling system used by the U.S. Energy Information Administration, EIA, to project energy production, consumption, and prices. The NEMS system contains 3 main parts. A central database to store and pass inputs and outputs between the various components. Energy modules that represent various demand, transformation, and supply projection activities. An integration, or convergence, module that determines when the system has reached an equilibrium between supply and demand. The modules represent each of the fuel supply markets, conversion sectors and final consumption sectors of the energy system. The modular design also allows for the most appropriate methodology and level of detail in each energy sector. NEMS executes each of the component modules to solve for the prices of energy delivered to end users and the quantities consumed by product, region, and sector. The prices delivered for fuels cover all activities necessary to produce, import and transport fuels to end users. Information flows also include areas such as economic activity, domestic production, and international oil supply. NEMS consists of the following components: 4 supply modules, renewable fuels, natural gas market, oil and gas supply, and coal market. 4 demand modules, residential demand, commercial demand, industrial demand, and transportation demand. 2 conversion modules, electricity market, and liquid fuels market. 1 module to simulate energy or economy interactions, macroeconomic activity. 1 module to simulate world or domestic liquids interactions, international energy. 1 module to calculate carbon dioxide, CO2, emissions from fossil fuel consumption and non-combustion uses of fossil fuel inputs, emissions policy. 1 module that provides the mechanism to achieve a general market equilibrium among all the modules, integrating module. To represent regional differences in energy markets, the component modules of NEMS function at a regional level. For instance, NEMS publishes end-use consumption and prices in its demand modules by 4 census regions and 9 census divisions. The Natural Gas Markets Module, NGMM, is the component of the National Energy Modeling System, NEMS, that represents the North American Natural Gas Transmission and Distribution System. The module code is written in the AIM software package and is a quadratic program, QP, that maximizes consumer plus producer surplus minus transportation costs. The consumer surplus represents the amount of money saved by consumers who would buy natural gas at a given price but are able to obtain it at a lower one. The producer surplus represents the added revenue of suppliers who could sell natural gas at a lower price but are able to charge a higher one. Therefore, By maximizing this combined surplus, and subtracting transportation costs and subject to balance and capacity constraints, the model arrives at an equilibrium price for the market. Below is a detailed summary of this module. The QP solution maximizes consumer plus producer surplus, minus variable transport costs. The objective function represents consumer demand as the sum of the areas below the LNG export demand curves for all LNG export regions. It represents production and transportation costs as the sum of the following: the area below the supply curves for all supply types and supply regions. Variable transport costs, which include the gathering charges applied to all flows from a supply region to a hub, as well as tariffs, represented by the sum of the areas beneath the pipeline tariff curves for all flows between hubs, like along transportation links. All volumes are in billion cubic feet, BCF, and all prices are in 1987 real dollars. All volumes are in billion cubic feet, BCF, and all prices are in 1987 real dollars. The decision variables for the NGMMQP objective function are the volume of each supply type taken from each step defining the supply curve for all supply regions under each tariff curve step for each flow arc. The natural gas that flows from one hub to another hub, all supply regions to a hub, all hubs to all demand regions, all hubs to all LNG export regions, all storage region to a hub, all hubs to a storage region. And the total volume of supply of each supply type taken from each supply region. LNG export demand that is met from each step of the LNG demand curve for each LNG demand region, as well as the fuel used for liquefaction of these volumes. The constraints of the NGMMQP are: supply accounting and supply mass balance, demand mass balance, flow balance at hubs, flow balance at border crossings for pipeline imports into the United States, flow balance at border crossings for pipeline exports out of the United States, LNG export demand mass balance, tariff curve quantity balance, storage withdrawal balance and storage injection balance, supply curve range, tariff curve range, LNG export demand curve range, flow capacity, natural gas, NG, regions used to report regional flows and capacity, NGMM natural gas pipeline network representation. NGMM results are generally passed to other NEMS modules as annual totals or quantity-weighted annual averages. While the NGMM and the NEMS oil and gas supply module, OGSM, pass expected or realized free production, associated production, and supply prices to each other by OGSM district, of which there are 84, these results are ultimately passed to the NEMS by oil and gas supply region. There are 14 regions, 7 onshore regions, 3 offshore regions, 3 Alaska regions, and a U.S. total. The decision to build additional LNG export capacity in each demand region is projected as described above, outside of the OGSM-QP. The OGSM-QP project's capacity utilization, including that of new capacity built, and LNG export volumes. Because the OGSM-QP decision variable for export volumes also includes the natural gas consumed during liquefaction, the module disaggregates the two volumes. It first computes the area under the LNG demand curve, then multiplies this total volume by the assumed percentage of the export volume required to liquefy the natural gas. The utilization of existing LNG export capacity is projected using a linear demand curve as shown in the figure. For Alaska and Western Canada, the two regions where LNG exports are not considered part of NGMMQP, it assumes that the LNG export capacity is fully utilized. In both cases, it is not the supply price of natural gas that determines market competitiveness, rather, it is the comparatively high capital cost of the liquefaction projects, including the new pipeline infrastructure required, that would make building new LNG export capacity uneconomic. Their locations on the Pacific coast also mean that shipping costs to Asia are much less than the shipping costs for LNG exports from the Gulf Coast. Therefore, once LNG export facilities are built, LNG from Alaska or Western Canada would be expected to outcompete all other global LNG supplies on a variable cost basis. The corresponding fuel used for liquefaction in Alaska is included in the U.S. Total fuel used for liquefaction is not explicitly calculated for Western Canada. For all natural gas flow arcs, the flow in the arc is equal to the total volume of implied natural gas times the utilization of the arc capacity. For example, the flow from center to center is equal to the volume implied by the amount of the fare curve on that arc. For each arc between two sites, a fare curve is created to represent the variable cost of transportation per unit of flow, based on capacity utilization, minus the cost due to pipeline fuel used during transportation. These curves are based on historical spreads between the spot prices of both centers. The chart presents the services NEM should offer by 2050. Minimum cost dispatch with market restrictions. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. This model was implemented by Hypothalamus Artificial Intelligence, HI, when the electricity market was liberalized in Colombia, in 1995. Considering the function of a regulator. The idea of regulating a market is to improve its behavior. Therefore, an imperfect market must be regulated to achieve a perfect market. What does not seem logical is that a perfect market would be regulated and become an imperfect market. The traditional is that a regulation is drawn up, and from it the models that represent the market are built. However, what is scientifically correct is that there is a market model. It facilitates the verification of the validity of the regulation that is being developed. The starting point is a traditional model of economic dispatch, which determines the levels of activity of the infrastructure and the energy generated, simulating a perfect market with inelastic demand. The formulation of the economic dispatch model is the traditional one, and it must be the one used by the energy-producing agent. The regulation determines the levels of commercial activity, the commercial transactions, and the adjustments in the economic dispatch model. This model depends on the regulation of each region. The integrated model is the union of both models, which can be integrated as a monolithic model. The models integrate physical and commercial dispatch, and it must be ensured that the energy generated in the electricity system is equal to the energy negotiated in the market. The model could be conceived as a conversation between models. In the case of the Colombian market, the following concepts are introduced by the regulations, forming part of the regulated model. Ideal dispatch, price of scarcity, electricity supply contracts, fuel supply contracts, reliability charge, firm power options, and plant start-stop. This model changes dynamically, as regulations change. Other entities that are part of the Colombian regulations. Reliability charge, specifically, the FPO, firm power options, allocations of each of the plants during the given horizon periods. Long-term electricity trade contracts, contracts under specific forms to guarantee future delivery of electricity. Gas supply and transport contracts, take-or-pay contracts, or other types of standard or bilateral contracts, for the supply of gas to different market agents. Strategic bidding, price makers, and maximizing revenue. Strategic bidding under uncertainty is a decision-making framework used primarily in high-stakes, deregulated environments, most notably electricity markets, where participants must place bids without perfect knowledge of their rivals' behavior, market demand, or external variables like weather. In strategic auctions, uncertainty usually arises from three areas: competitor behavior, lack of information regarding the marginal costs and bidding strategies of rival firms; market volatility, unpredictable fluctuations in demand, clearing prices, and transmission network constraints; exogenous factors, short-term events such as plant outages, variation in renewable energy inflows, wind or hydro, and load forecast errors. The strategic bidding problem, BSP, is usually formulated as a bi-level optimization problem, which in turn is transformed into a nonlinear programming model using Karush-Kuhn-Tucker complementarity conditions. Since the resulting problem is highly non-convex, an intensive search for efficient solution methods has been carried out. To avoid the above difficulties, BSP has represented the non-convex residual demand function in a Carnot scheme using a mixed integer linear programming (MILP) model. This allows you to calculate the optimal bidding strategy in a single bus environment, including unit commitment, as illustrated by examples derived from the Spanish system. In addition, the residual demand function is also represented by a MILP model that takes uncertainty into account, establishing residual demand scenarios for the day-ahead market session. The generators are associated to competitor firms explicitly modeled, instead of using the residual demand function, and use an alternative MILP formulation, based on a binary expansion, B, of the decision variables, price and quantity bids. In 2008, Hypothalamus Artificial Intelligence developed the same model for the supervisor of the Colombian electricity market, to analyze the exercise of the dominant positions of generating agents. Once the price and quantity offers of the agents have been submitted, the market operator carries out an economic dispatch, ED, to clean the market and determine the spot price and the generation cent. There is no possibility for an agent to modify its offer once the ED has been executed. The generators are associated to competitor firms explicitly modeled, instead of using the residual demand function, and use an alternative MILP formulation, based on a binary expansion, B, of the decision variables, price and quantity bids. DA is formulated as a linear problem where the objective function is the sum of the offers, lambda, multiplied by the quantities of all the generators. The sum of electricity supplies must equal demand, and estimated generation cannot exceed capacity. Associated with constraints 2 and 4, there is a set of Lagrange multipliers pi, the spot price as the marginal cost of increasing the load supply and the marginal benefit of increasing the generator's supply quantity. The starting point is the ideal ED dispatch model, which does not consider the transmission system. The complete ED vision includes the dual feasibility zone, and the complementary slack conditions. Each generator receives a gross revenue, or operating profit, given by the product of spot price and its energy production. The net revenue of an agent is obtained by deducting the variable operation cost from the total gross revenue, where Cj is the variable operation cost of plant J. The goal of the set A of agent is to get the combination of price and quantity bids that maximizes their total net income. The spot price and energy production in the objective function result from the economic dispatch, which in turn depends on the price and quantity supplied. The strategic bidding problem is a B-level optimization problem that, in addition to the primal variables, uses dual results from the economic dispatch. The first step in solving it is to write the optimality conditions of the second-level problem, ED, as part of its constraint set. The problem can be solved as a nonlinear complementarity problem, NCP, that ignores ED objective function. Some approaches consider using integer programming to solve a mathematical programming with equilibrium constraints model, PEC. In terms of agents, the dual objective function is equivalent to maximizing their revenue. The problem in dual terms is equivalent to a nonlinear programming problem, NLP. The structure of the strategic bidding problem is shown in the diagram. The maximum revenue problem can be solved with solvers for the following types of problems: nonlinear programming problem, quadratic programming problem with quadratic constraints, and mathematical problems with equilibrium constraints. If you don't have access to the right algorithms, the problem of strategic tendering is difficult to solve because of the products of variables in the objective function and in the primal dual equality constraint, or slack complementary. The proposed solution approach is to transform those products into binary linear expressions. The product is eliminated by rewriting it in terms of the other products, such as equation 26. Equation 27 allows us to replace the product by the linear expression on the right-hand side. Equation 28 allows other products to be transformed into a conditional equation. This transformation allows conventional solvers to be used to solve the problem. The problem of the equation 35 to 49 is a mixed linear integer problem, which can be solved by GNU or commercial solvers. The accuracy of the model solution depends directly on the value of M1 and M2. The bigger these values, the more precise the model will be. However, a trade-off between accuracy and computer time should be considered. Also, since M1 is a power of 2, then as the value of M1 increases, the target value does not decrease. The same goes for M2 and E2. The main advantage of the binary model, MIP, over the nonlinear model, NLP, is that the nonlinear model can be non-convex and therefore can have multiple local optima. The binary model ensures convergence to the global optimum. As a disadvantage, it is quite likely that the binary model will require more time than the nonlinear model. Suppose that the bids of the generators and the load are uncertain and represented by a set of scenarios, with probabilities. The so-called risk-neutral strategic bidding problem is formulated using equations 50 and 51, maximizing the expected value of revenues. High considers that maximizing expected value is a very risk-prone position, and that it is not correct to call it neutral. Financial risk control should be included to manage risk and select a position that is consciously averse or prone to risk. Brazilian System Overview in 2003. Generation System. Brazil's surface area is equivalent to that of the continental United States plus half of Alaska. It has a total installed capacity of 83 gigawatts. Hydropower generation accounts for 85% of installed capacity, with 110 hydropower plants arranged in complex topologies along 12 major river basins. 28 thermal power plants, including nuclear, natural gas, coal, and diesel power plants. The generating plants include some large ones, such as Itaipu, with 12.6 gigawatts, and Tucuruí, with 8 gigawatts, several medium-sized plants, in the range of 1 to 2 gigawatts, and the rest between 100 and 500 megawatts. The entire country is interconnected by 70,000 kilometers of high-voltage transmission lines. Sectoral reform. It began in the mid-90s, with the privatization of most of the distribution companies and the creation of the regulatory agency of the national system operator and the wholesale energy market. In 2002, the second phase began. The government authorities investigated the implementation of a price bidding system. To address concerns about the effects on the operation of cascade hydropower plants, several analytical tools were developed, including a market simulator, a Nash equilibrium model with stochastic dynamic programming, and a model to simulate the competitive operation of cascade hydropower plants. The bidding model has three key entities. Strategic bidder. The Brazilian generation system is composed of 11 companies, located in 4 zones. The bidding agent Companhia Energética de São Paulo, CESP, controls 5 hydro plants, with a total capacity of 6,900 megawatts, 8% of the system's installed capacity. Strategic bidder model. A pure price bid model was used, that is, only prices are decision variables for CESP, the bid quantities are the generator capacities. The pricing decisions of each plant were divided into 128 segments in the range 100 to 300% of the respective water value. Bidding scenarios. The bidding scenarios include total load and price and quantity bid for the remaining 133 generators of the system. 10 bidding scenarios were created by randomly sampling the following parameters. Load level, sampled from a normal distribution with coefficient of distribution 10% around the predicted peak load. Quantity bid. The capacity of each generator was sampled from a binomial distribution for the forced outage rate. CESP's plants were assumed to be available, and price bid were kept constant and equal to the water value, in the case of hydro plants, or variable operation cost in the case of thermal plants. The water values were calculated following the same approach used for CESP generators. The table shows the plant names, capacities, and variable operating costs. The water values were taken from a stochastic hydrothermal scheduling model like the one used by the Brazilian national system operator. The table presents the optimal bid prices. Uncertainty depends on the availability of other agents' plants, however, it can also be modeled by different methods, such as the use of historical information. In this context, one possible approach is to predict the behavior of the demand of the day under study and use a clustering method to select past days sufficiently similar to this one. Then, each of these selected days would form a scenario for price and quantity. Table 2 compares the B price bids with the operating costs of Table I. These price bids form the bidding curve that SISP supplies to the market. Only two generators, Jaguari and Isolterra, had bid prices that were different from their respective costs. Energy production, in megawatts, and spot price in Brazilian reais per megawatt hour. Keep in mind that using different sampling methods may produce different results in scenarios. Thus, because the optimal bid strategy obtained by the model is compatible with the set of scenarios considered, considering a different set of scenarios will lead to a new optimal bid strategy. The table shows the production of each plant and the spot price in each of the 10 scenarios used in the optimization. The optimization is carried out for a single hour. The stochastic B model has binary variables for each of the 5 plants. The total number of integer variables is, thus, equal to 40. There are 2,694 continuous variables, the spot price and the generation of each plant in each scenario, other dual variables, and 2,545 constraints. For each scenario, the chart compares spot prices for 2 models, optimal bidding and cost-based bidding. You can see the increase in the spot price for the optimal bid model. For each scenario, the graph compares the electricity generation of 2 models, optimal bidding and cost-based bidding. You can see the decrease in the generation for the optimal bid model. The figure shows the difference between the net revenue obtained with the B model price bids and cost-based bids in each scenario. The results are consistent with the theory. Smart grids, bi-level programming and Stackelberg equilibrium. This section is based on an optimal real-time pricing for smart grids, a bi-level programming approach. Bi-level programming, VLP, is a hierarchical optimization approach where one mathematical problem is nested within another. It is widely used to model interactions between 2 decision makers, a leader at the upper level and a follower at the lower level. The leader chooses a strategy first, anticipating that the follower will react optimally to that decision. The follower optimizes its own objective based on the fixed decision provided by the leader. The modeling on optimal real-time pricing, RTP, for smart grids frequently uses bi-level programming to model the interaction between utility companies, leaders, and customers. The B-level programming approach to model interactions between utilities and their customers is: first, an electricity bill minimization model, lower-level model, should to incentive the customer to change his electricity use pattern. Second, a profit maximization model, upper-level model the utility. A branch and bound algorithm is chosen to solve this proposed bi-level programming problem. As the simulation results show that both the retailer and the customer can benefit from the proposed framework, it has great potential to improve the implementation of current energy pricing programs, help customers to reduce the increasing energy bills, and change their energy usage patterns. This model can be extended in several directions. First, the lower-level problem considers the trade-off between minimizing bills and satisfying customers' comfort. Second, the real-life problem must be extending the current multiple followers. The image presents the detail of the background of the bi-level programming theory for the case of interest. The lower levelized cost of electricity from photovoltaic, PV, systems compared to residential retail tariffs has incentivized households in many countries to invest in rooftop PV systems. Similarly, advances in battery storage systems are making them economically viable for use by electrical consumers. Thus, a combination of domestic energy storage and rooftop PV systems has proven to be cost-effective under various regulatory schemes, which has led to the emergence of so-called prosumagers, consumers with potential for electricity generation and storage, as new market players. With the expansion of smart grid infrastructure, several innovative demand response models, DR, seek to address these challenges. The focus of these business models should be the provision of incentives compatible with the needs of the system. The most common DR schemes instruct consumers to change their consumption patterns, upon request or under a contractual agreement. The figure shows a schematic overview of the prosumagers model. The process simulates a simple case of an energy distributor, a typical single-customer electric utility, which is supposed to have 4 appliances: dishwasher, washing machine, dryer and FEV. The programming horizon is from 8 a.m. to 8 a.m. in the morning the next day. For the cost of energy supplied to the customer, the model uses a linear cost function, which represents the amount of energy supplied to the customer at each hour of the day. The aim of RTP scheme is to find the optimal 24 hours prices by maximizing the utility's profit, upper level problem. Besides this, with this identified price information, the customer can achieve his best benefit, minimizing his payment bills, lower level problem. The smart grid energy provider is assumed to be an electric utility. The table shows the parameters of the appliances, which are S. Demand on a typical day, H is hours of consumption on a typical day, and the minimum and maximum power level. The table shows the optimal 24-hour prices offered by the power company. The figure shows the optimal real-time prices offered by the power company. Getting ideas from the time of use pricing, TOE, we divide the 24 hours prices into 3 levels: peak hours, between the 5 p.m. to 12 a.m., mid-peak, between 8 a.m., and off-peak, between 12 a.m. to 8 a.m. For peak hours, the prices range from 12 cents to 14 cents, for mid-peak hours, while the prices float between 6 cents to 10 cents for off-peak hours, from 8 cents to 12 cents for mid-peak hours, while the prices float between 6 cents to 10 cents for off-peak hours. The diagram presents the bi-level programming scheme for the Stackelberg equilibrium. To make it more manageable, the hierarchical problem of bi-level programming becomes a single-level problem, replacing the lower-level problem with its Karush-Kuhn-Tucker conditions, KKT, which makes it a mathematical programming with equilibrium constraints, known as MPEC. The problem can also be solved with other algorithms, such as the proposed branch and bound algorithm. Figure shows energy consumption comparison with scheduling and without scheduling under obtained optimal real-time pricing. To design a benchmark, we assume that, without our proposed optimal programming scheme, appliances start operating right at the beginning of time and at their usual power level. The comparison of the energy consumption of appliances with and without scheduling can be seen in the figure. The results indicate that if the customer changes energy consumption from periods of high price to periods of low price, the proposed scheduling scheme causes the customer's electric bill for one day is reduced from $2.35 to $1.94. This presentation describes a dynamic, oligopolistic, spatial, Nash-Kernot equilibrium model to determine hydroelectricity dispatch and spot prices, of medium and long term in an open market, integrated by a spot market, and a long-term market for financial risk hedging. The thermal generators participate in a long-term market of fuels, in the one which they buy gas subscribing long-term take or pay contracts. The model determines the electricity dispatch, the electricity flow, the spot price, and generator spot market bids. The model considers that each generator acts as a Nash player, maximizing its revenue based on the optimal determination in each period of the quantity of generated energy, the quantity of bought, or sold, energy in the spot market, and the prices offered in the spot market. The behavior of each generator is simulated based on an individualized model that represents its industrial infrastructure and financial hedging instruments and bilateral contracts. The spot market, or the market operator, is considered an efficient agent that minimizes the costs of attending the demand according to the prices offered by the generators, and it is represented by an integrated model that considers all the physical constraints of the system and guarantees the feasibility of electricity dispatch. The two models are integrated based on a hierarchical relationship in which the spot market is the coordinator of the offers and decisions of the agents. The exchange of information between the two levels is based on the price offers accomplished by the spot market, and offers accomplished by each generator. The integrated model can be conceived as the coordinated sum of the physic model and the trade model. The physic model represents all the existing relationships between the different components that make part of the production infrastructure, and the trade model represents all the conditions accepted between the agents, buyers and sellers, to accomplish commercial transactions endorsed by their physical infrastructure. The equilibrium model has two levels, The first is related to the competitive spot market, and the second is related to the market agents who are simulated individually as Nash players. The spot price model corresponds to a minimum dispatch model, with physical and commercial restrictions, and Nash player models are maximum revenue models with commercial and infrastructural constraints. The models represent rational positions for generators and for the spot market and are solved in a coordinated manner by determining the market break-even point. The spot market acts as coordinator and the generators as coordinated agents. The spot market sends signals to the generators, the spot price, and the generators send signals to the spot market, their bid offers. Spot market model. The characteristics of the physics system presented in the spot market model are: the transmission system represented by electrical operative areas and by transmission lines that interconnect them. The consumption centers and the generation units located in the electrical operative areas. A transportation system with nonlinear losses is considered for the energy transmission. Hydraulic generation based on constant conversion factors. Hydraulic topology detailed. It corresponds to a traditional model of economic dispatch. The commercial system is based on the following hypothesis. The financial instruments and the bilateral contracts are consolidated by each generator. The industrial infrastructure of a generator may be composed by multiple hydraulic plants and multiple thermal plants. The thermal generator has taken or paid contracts for gas supply. The following entities are used in the integrated model: generator agent, electrical operative area, electrical restriction, reservoir, group of options, hydraulic plant, thermal plant, transmission line, electricity consumer node, and period. Physical and commercial models integrate the spot market model. The spot market can be considered as an agent that represents the consumers, the demand side, and whose function is to coordinate all the Nash generators to satisfy the system demand. The economic rationality of this agent is based on the principle of attending the demand minimizing the caused cost. The spot market must guarantee that the physical restrictions, due to the technology and to the topology of the interconnected hydroelectric system. Electricity market regulators have different conceptions of what an open electricity market should look like, so the models depend on these case-specific conceptions. In this case, an electricity market regulated according to the following principles is being analyzed. In this case, the spot market allocates generation rights based on an ideal system, that does not consider the limitations of the transmission system. There are no variable loads per transmission. This is because all the energy is sold to the ideal system. The spot market can be considered as an agent that represents the consumers, the demand side, and whose function is to coordinate all the Nash generators to satisfy the system demand. The economic rationality of this agent is based on the principle of attending the demand minimizing the caused cost. The spot market must guarantee that the physical restrictions, due to the technology and to the topology of the interconnected hydroelectric system. Nash generator model. To optimize decisions in the spot market, the signals of the generator, the bid of the plants for generation in the spot market, are required in each period of the planning horizon. Each Nash generator determines its optimum decisions having as reference its expectations with respect to the spot price. The agent tries to maximize its revenue for the planning horizon of the T periods, determining the optimal quantities for self-dispatch generation, spot market purchases, and the spot market purchase price of its energy. The problem that each generator must solve is a function of the expectations regarding the spot price vector for each period of the planning horizon. To determine the commitments acquired by the generator, it should consider the energy committed in the long-term market. For example, the options commitments will be effective depending on the relationship between the spot price and the option strike price. To represent the previous situation, it should consider that the generators support groups of options that are characterized by the option strike price, OSP, and the quantity of energy negotiated, N. The Nash generator must carry out an ideal private dispatch, including its physical model and its business model, thus determining the value of its resources. For the infrastructure constraints, In the case of hydraulic plants, it is necessary to consider continuity equations that govern the hydraulic system. Final level equal to initial level plus runoff minus generation plus reservoir movements minus spillage. For each period T, the generator variable income can be expressed as the sum of the sales in the spot market, the options, futures of bilateral contracts exercised by the buyers. The text shows how the amount of power can be calculated in the options that the generator must deliver. The most general case of the above equation can be expressed as indicated in the text. The problem to solve for each Nash generator is NAP. Nash agent problem. The dual NAP variables represent the income that would be obtained if the availability of resources, at the end of a period, is increased by 1 unit. To determine the bid to the spot market and maintain the same level of revenue, the cost of using the resource must be added to the previous benefit, which in hydroelectric plants is normally assumed to be 0. Therefore, the bid to the spot market for each plant must be defined using the dual variables. Generators with hydro resources must determine the bid spot market, considering the opportunity cost of using the water resource in a period in exchange for the possibility of its use in the future. This opportunity cost is determined by the dual variables of the constraints related to the availability of water resources at the end of the period. MPEC, Mathematical Programming with Equilibrium Constraints. Case, Modeling Competition in Electric Energy Markets by Equilibrium Constraints. Around the world, the electricity industry is undergoing a significant restructuring towards deregulation and competition. Under this new framework, electricity companies assume more risks and are more responsible for their own decisions. Utilities need original models that meet these new requirements. This paper presents a conceptual approach to modeling deregulated electricity markets. It combines powerful traditional tools related to the detailed operation of the system with techniques to model the equilibria of economic markets. The proposed approach models the competitive behavior of electricity companies by incorporating a set of constraints, specifically equilibrium constraints, into a traditional production cost model. These constraints reproduce the optimal first-order conditions of the strategic companies. The approach achieves a goal of maximizing profit while maintaining the details of the system's operation. The model was implemented in GAMS and is of the Mathematical Programming with Equilibrium Constraints, MPEC, type. The diagram shows the scheme of the production cost model with equilibrium constraints. The production cost model performs hydro, maintenance and fuel scheduling, seasonal operation of pumped hydro units, weekly and daily operation of pumped storage units, and thermal unit commitment for a generation system. The target function to be minimized is the total variable cost for the scope of the model and is subject to operational constraints. These can be classified into inter- and intra-period constraints, according to the periods that are involved. Interperiod are associated with the coordination of limited production resources, minimum quotas of fuel consumption, hydro inflows, and seasonal pumping, storage, generation, and intra-period deal with the system operation in each period, balance between generation and demand, thermal unit commitment, weekly and daily pumping and storage, and all the generation limits. Market equilibrium constraints imply minor modifications to the previous optimization problem. An important change in a traditional model of production costs is the introduction of elasticity of demand, as a response of demand to the price of energy. In classic models, demand is inelastic and must be covered, subject to a penalty for uncovered load. The equilibrium quantity is obtained by maximizing the total surplus, defined as the sum of the consumer and producer surplus. In fact, maximizing the total surplus is exactly equal to minimizing the area below the supply curve to the left of the equilibrium quantity, accepted generation, and below the demand curve to the right, non-served demand. Below is a summary of the equilibrium constraints. Equation 2 can alternatively be expressed as the level of generation that, for each firm, maximizes its profit as a function of the short-term marginal price, SMP, its marginal cost, and the slope of the demand curve, which is negative. The previous market equilibrium model implicitly assumes that there are no operating constraints. The firm's profit maximization problem, subject to the operating constraints, can be solved by constructing the Lagrangian, and then formulating the Karush-Kuhn-Tucker, KKT first-order optimality conditions. The market clearing price, SMP, is represented in two different ways. As a constraint, it is modeled by a linear function of electricity demand. In the objective function, such as the term non-served demand costs, SMP is transformed into a stepwise decreasing function, with the same slope as the linear function, where each step is a fictitious demand supply. This second modeling approach is used to avoid nonlinearities in the objective function. The above equilibrium constraints incorporate market behavior into the classic problem of minimizing variable costs, while maintaining all the details of the system's operation. The figure shows the theoretical market equilibria achieved under both frameworks of the model objectives, cost minimization, CM, and profit maximization, CE. The upper side presents profit as a function of the firm's output, explicitly showing that production in the case of oligopoly is reduced to increase profits. The lower side presents the different market equilibria obtained at the point of intersection of the step curve of marginal cost and the demand function. The table shows the summary of thermal and hydro capacity of each firm. The generation system is composed of 18 generating units belonging to 3 companies of different size, structure and technology mix. Each firm has several thermal units, but only one has a limited energy hydro plant. Firm A has 7 thermal units with 7,000 megawatts of installed generation capacity. The production costs go from 15 to 32.5 and $35 MWh. Firm B owns 6 thermal units with a capacity of 5,500 megawatts and another hydro unit of 3,000 megawatts. The thermal production cost ranges between 17.5 and $35 MWh, and Firm C manages 5 thermal units of 3,500 megawatts and a cost range between $25 and $35 MWh. The figure shows the aggregate variable cost curves of each firm, which are its supply functions. The hour-by-hour demand profile corresponds to a weekday with a maximum of 19 plus 000 megawatt and a minimum of 8,000 megawatts. Each demand level is represented by a linear function of the price. The slope of the demand at every hour is $5 MWh/GW, which provides price elasticities of around 0.6. The figure shows the daily demand and price profiles obtained by the model in a perfect competition framework. The results show how firms A and B increase their profits by restricting their generation. Their large size allows them to compensate for the decrease in production with an increase in the income obtained with the remaining generation. However, Company C, which is smaller, increases its production in the second case, because the optimal for this company is to produce as much as possible. Due to its smaller size, a potential price increase does not compensate for the revenue lost from the remaining restricted generation. Its profits are maximized by behaving like a price-taking company. In the graph on the left, the strategic position of companies raises the price when it is compared with a non-competitive position that maximizes the social surplus. In the graph on the right, generation is restricted by companies to increase the price. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.